is we're going to do one of these gas power cycles, and probably we'll do there's some of the others that are already, you can see the solutions. So the one that doesn't have solutions for the gas power cycle, of course you already had midterm 3. We'll do this dual cycle. Okay. So we'll cover the dual cycle and get the solutions to it. Before we do that, and then after that, of course, after we do that, we'll finish up basically chapter 9. Then we're going to go into chapter 10 on combined vapor gas power cycles. If you've looked at the example final exam, you're going to find that there's a problem related to this, or several problems related to chapter 10 in the final, okay, if you looked at the practice. In the meantime, let's get the solution to the midterm glass of water. So I'll just write the energy and entropy balance associated with that so you can see it. And then we'll go to chapter 9, gas power cycle. So some of the grades have already been graded already related to midterm 3 laws. But nevertheless, you had the problem where you had a glass of water or a ceramic cup. Okay. And this ceramic cup was in a refrigerator. And the pressure inside the refrigerator was same as atmospheric pressure, so I'll put P naught. And then you had some refrigeration temperature, and this ceramic cup was filled with water. So you had a ceramic mug filled with water. Of course, inside the refrigerator, outside the refrigerator, you have T naught, P naught, the temperature and pressure of Florida. Okay. If I want to do a boundary on this, I can draw a boundary around it, and let's put the boundary like such. So here's my boundary. Okay. And then what happens is you took the cup out of the refrigerator, and then it was placed on a table, and like such. Sometime later. Now it's very open-ended. You have state 1, and then you have state 2. Okay, and you're supposed to do an energy and entropy balance, but when do you decide is the final state is kind of left up to you. So you could say the final state is a week later on the kitchen counter. You could say it's 5 minutes later. It's up to you. In principle, you just define how it is, what your final state is. You know that it needs to be at equilibrium or at some close to equilibrium state, and the temperature and pressure of the surroundings did not change. Okay, so doing a boundary around it again, because that's the one thing you can have a change in boundary. Okay. You can define your final state with new boundary, a new size boundary, and we do that often in gas power cycles, right? You have your gas that expands, there's work on the gas, work by the gas, right, for engines and whatnot. So we have moving boundaries. That boundary does corresponding work on the surroundings or work on the system, right, compression of a gas. Okay, we'll just keep it like this, and we'll say that we can say that there's a small change in volume of our system or not, okay? But in this process, we end up, and one thing we do know is that TR is less than T naught, right? Inside your refrigerator is at a lower temperature than initially, okay? And so just from the standpoint, cooler water mug, warmer water mug, you know that there has to be some heat into the system when you go from state 1 to state 2. Then you can think about, so this problem, I like many of the students who came to my office asking about the solutions. One thing they did is they maybe didn't get full credit, but one thing they did do is they demonstrated that they're actually thinking about an energy balance with something practical. And almost everybody in here has, if you haven't thought about it, you've taken a container with some liquid in it at a cooler temperature and you've put it onto the counter, okay? Yeah, given that you live in the United States, there's refrigerators everywhere. So somebody's done that. And what have you noticed happens? There's some condensation that gets on the outside. Now, if I were to wait a week, okay, and you'd come back to this mug, what would happen? You'd basically have no water in it. It would all have been evaporated, right? So you went from a system containing ceramic and water to a system where it's just a ceramic mug at Tina. All the water would have left your boundary. So there's various ways you can do this. Also, we know typically materials have positive thermal expansions and coefficients. As they get warmer, they expand. There are some materials with negative thermal expansion coefficients. They're rather exotic, or they have some unique aspect to them. And ice, not necessarily a thermal expansion coefficient that is. Well, water is typically negative. As you cool it, it gets smaller. But water, when it goes through the phase change, it expands, right? So as you decrease the temperature, it expands a little bit. So that's a little bit, but that's kind of, we don't want to get there because we're not saying ice water. But the point is that you could have some boundary work. Okay, so for just doing this, and we could have some mass transfer associated with condensation, or mass transfer associated with evaporation. Plus we could have some P delta V boundary work. Okay, so those who got close to full credit probably said neglecting boundary work, no evaporation, right? Just a little bit of condensation. They wrote in words and explained what they would see, okay? So let's just do a general energy balance. For the problem, sum of all the forms of heat in, plus the sum of all the forms of work in, plus the sums of all the forms of masses in, and each mass has a corresponding, if we were to look at it, having a kinetic energy, potential energy, and then some internal temperature pressure energy encompassed into the specific enthalpy, okay? And so this would be all the forms of energy in from going from state 1 to state 2. And then we have all the forms of energy out, all the forms of heat out, all the forms of work out, and all the forms of masses out. And I'll just put ... because it corresponds with the J. And then that has to equal the sum of all the changes in internal energy of the types of material within your boundary. So if you want half credit on this part, you would just write this, okay? Some students did that. I'm still seeing that many students don't know how to write this correct, or they're making mistakes. And with that said, even the ones who are making mistakes here, they get something relatively decent after. But I'm a little confused how you get there if you can't write a general. Right? And as I said in earlier lectures, what happens later in your coursework or later in your career, in essence, all these sums become integrals. You have a distribution of masses. It's not just, they all become integrals. Or you take a derivative of this and you can get a differential equation. And in fact, when you take heat transfer, that's exactly what you're going to be doing. You're going to be looking at just the heats in and out of a system, and you're going to be taking derivatives of things to get the heat fluxes. Nevertheless, half credit like such. Well, let's consider the case where we have a little bit of condensation and we have a little bit of evaporation, and also the cup expands a tiny little bit. Okay? And in that case, what is my system composed of? Well, basically inside the boundary doesn't change. We could say, we could even make it more complicated. We could get some, we could have really pure water, and we could say that there's carbon dioxide that dissolves into the water. Okay, you could go through all the chemistry stuff and things you can do, but we're not going to do that here. We're just going to keep it as K equals 1 ceramic and K equals 2 water. Okay? And then heat in. Yes, from practical side, there's some heat in, so let's just say we have some Q in. Now, so when I talked to some students, they said that there was some heat in, but they put two forms of heat in, one associated from the counter into the cup and one associated from the air into the cup, which is fine. You can do that if you want, or you can just say that there's some net heat into the system, okay? And then work in, is there any work into the process? Well, if you didn't know if it was boundary work in or boundary work out, you didn't know how it expanded, right, in the process, you could just put network in and then use the interval form, okay? But in reality, both water and the ceramic expand when they heat up, so it's going to be boundary work out. So let's cross this out. And then the mass is in. Well, you take that cup, you put it on the counter, then it's a decision. Of course, you're going to get little bits of condensation on the side. Do you say that condensation happens within the boundary? So you have some condensate, do you say it's on the outside of the boundary? Well, for the time being, let's just say that the condensation is really small and it stays within the boundary. So we have some mass in. So I equals 1 water condensation. Okay? And then heat out. Well, when you have a bell curve, okay, and just as an example, we have P and V. If I'm over here, what am I? Saturated vapor, superheated vapor. If I go from here to here, I condense all my vapor, saturated vapor, into saturated liquid. I take basically steam at saturation temperature and pressure, and I condense it into liquid. Or the other way around, if I go the other direction, this is what we do on a more regular basis. We go this way. We go from saturated liquid to here. You put a pot of water on the stove. You add heat. It gets to the boiling point, and then you start to see vapor leaving. So what did you have to do to go from here to here? There was some Q in to boil liquid. You add heat. Well, the same has to happen if you go in the other direction, and we have had cycles with condensers and things to take a liquid and to condense it from water vapor to liquid condensate. You need to remove heat. Okay? So there had to be some heat removed from the liquid. Well, what removed the heat from the liquid? The ceramic cup. The heat had to come from somewhere. To take vapor and turn it into liquid, you have to condense it. It means you have to remove heat from the liquid. But where did the heat come from? It had to come from the ceramic cup. So there was another Q in for condensation. Okay? Now granted, the condensation isn't, yes?
I was going to ask, if in our assumptions we put that condensation had not formed yet, would that exclude
You said condensation did not form yet. Perfect.
Okay.
I'm just putting out that this is what I want. I want you guys to think about it and make justification why you did what you did on your energy balance. That's the most important thing about this. Yes, getting 20 out of 20 or 10 out of 10 and all this stuff is great, but what's the most important thing? You're thinking of what actually happens and what you see in reality, and you're comparing it to an energy balance that you're establishing, or an entropy balance. And you're justifying why you do what you do. Those justifications can be wrong, but if you just write no justification on anything and you write an equation, that's exactly what I don't want to see, because it shows that you're not thinking about it. I want you to demonstrate that you're thinking about it. And I'm sure your employers later on are going to want to demonstrate that you're thinking about what you're doing in writing and verbally. And of course, they're going to probably your pay is going to be dictated by how logical your writing and your verbal thinking, right, communication and what you're doing is going to be. So this is just kind of an exercise for you to justify why you're doing what you're doing. Okay. So we have some Q in just for heating it up, and then there was some Q in for condensation. Well, that happened, but then if we consider that there was condensation and then the condensate evaporated, so you would have a Q out from condensation, right? And then if you said some liquid evaporated, you would have some Q out evaporation. Now, when I look at this, if I do the problem from taking it out, condensate's there, then later condensate's gone and water's evaporated, what had to happen? The same heat that went to condensation had to be that for evaporating the condensation. So these things will end up balancing out, the out and in. But if you were to say you just took it out and you got condensation there and then you stopped, then this wouldn't be here and you wouldn't have any evaporation. So there's a lot of different ways to do it, but right now we'll just keep it like this, and then we have some, do it, J equals 1. The only mass that could leave would be water evaporated. Yes?
So what is the first Q out there say?
Condensate.
Or what is the second one?
Evap.
Okay.
Q out, evap. And condensate. So I can rewrite the equation. Or you can say, hey, took it out, did it so quick that all that happened was it cooled down a tiny little bit, and there wasn't time for condensation or evaporation, and then what would it end up being in that case? Qn equals the sum delta U, okay. But you would have to justify. Now, of course, one thing I didn't do is this boundary work. Okay, so it got bigger. So also on this piece, right, you have some P delta V. It was expansion at constant pressure, but it expanded a little bit. That's basically the change in volume of your system. Of course, if you were to measure it, if we did this experiment, you would see that you wouldn't even be able to measure it without some really sophisticated instruments on how much the ceramic expanded. Because it's only going to be 20, 30 degrees, and the thermal expansion coefficient is 10 to the minus 6 per Kelvin. Right? So it's really small. It's going to be microns. You know, width of hairs, expansion. That's how much it would expand. So you wouldn't be able to measure it. But anyways, I'm pointing out this whole process of that. So for the time being, let's just use this one, right, as a circled in, and we said no condensation or evaporation. And boundary work is small. Okay, entropy balance, yes.
So that would be right if we justified it?
Yeah, if you justified it, yeah. You said you took it out and you measured it within 1 minute before condensation, or 30 seconds. All that would happen, well, the reality is, it's not quite right, because in that short amount of time, there wouldn't even be much time for it to cool down. The time it would take to cool down a degree is equivalent to the time it would take for condensation to form on the surface. But the main point is you might not get full credit, but you're going to get something close to 10 out of 10. So I have to take points off, otherwise, what am I saying? I'm giving you full credit, so paying attention to everything doesn't matter, because I'm just going to give you full credit, but yet I'm telling you to pay attention. So in order to back that up, I have to not give full credit unless you really justify things. But as the Air Force engineer would say, your A is right here, not the 10 out of 10 on this problem. Your A is how you apply your knowledge after you get your degree in the real field. And so that's what they're going to want to see. Okay, so now if we go to entropy balance, this is where remember this QN and QN condensate and Q out condensate and Q out evaporation? This is where, even though these will be equal, the boundary temperature is different during the two processes a little bit. So in the entropy balance, it actually matters that you separate these two. So of course, I'll write out the full entropy balance with everything we have here, and then I'll do a square one where we just neglect everything. Okay, so again, summation notation, all the forms of heat in over a corresponding boundary temperature in, plus all the forms of masses in, and there's a corresponding entropy per unit mass of the masses in, and then all the forms of heat out over relative to the boundary temperatures of the heat out, and all the forms of masses out, and the entropy per unit mass of the masses out. Okay. And then plus the entropy generated in the universe has to equal the sum of the change in entropy relative to all the forms of masses within inside your boundary. So of course K equals 1, ceramic K equals, so this still applies. And then if we go from this context, right, we have some Qn over some TB in, right? And this one would related to sensible heating. So if we look at the boundary temperature, it is not a constant. It changes, right? It's constantly increasing because it goes from TR. So the boundary temperature also is a function of time, right? And this is where the integral will come into play later. But nevertheless, we don't need to do all that. We just say TBN for sensible heating, and then we have some QN, right, for the condensation, and then we have some TB condensation, and then we can say that there's some mass in for condensation and some entropy per unit mass for the condensation, and then minus Q out, right, for condensation over TB condensation, where really it's the condensation evaporating, right? For evaporation. And then some Q out for the standard water evaporation over some TB evap. And then we have some mass out of the evaporated water and the entropy per unit mass of the evaporated water, plus S gen equals some delta S. Okay. Do I expect you guys to do all this? No, but it's the whole idea that even though you have what is seemingly a simple process, there's actually a lot that takes into place, right? And the reason for the summation notation is to try to figure out and to think about all the different forms of heat and masses that happen during a process from going from state 1 to state 2. Now, of course, if we do the same thing, no condensation, no evaporation, boundary work is small. It didn't matter here because there's no boundary work in the entropy balance. We could just get some Qn over some TBn, right? Plus S gen equals the sum delta S. So if you just wrote that with some justification, you're going to get close to full credit. But if you just blindly just say, write those two equations in the boxes, you're probably going to get, if you wrote the full summation above, a little bit over half credit. Okay. Any questions?
If you did not write the summations to differentiate between the materials, would that be very wrong?
Yes.
In your assumption?
Yes. Unless you drew a boundary, granted. This is where, as an engineer, you can be clever about how you solve things. Now, you have a differential equation, you change the boundary conditions, you get a different solution. Same thing happens here. You change your boundary, you look at a slightly different thing. So if I were to draw a boundary that was just around the ceramic, or you drew a boundary and you were just considering if I drew a boundary and I just considered the boundary associated with the water, and now my boundary was just of the water, then what's inside? Your system is composed of water, so you don't need a summation. Okay? But that's not what I was hoping you would do. I was hoping you would consider a boundary with both the ceramic and the water. But of course, you could make that argument. I made my system just the water in the cup. And you drew a picture with the water in the cup. Does that answer? There's many cases in engineering where that's the best way to get an answer to go on to the next step. Is just breaking it down to that one piece. Okay, that was kind of a long-winded solution to the energy balance. So now let's go to the dual cycle. So now let's do the dual cycle. And this will finish up chapter 9. So the dual cycle, chapter 9, gas power cycles. This is one where it's not quite given in the textbook, but they talk about it. And it turns out that this dual cycle, this way of doing it best, and it says here, the dual cycle represents the ideal cycle for a modern high-speed compression ignition engine, so basically a gasoline engine. So this way of describing it is the best simple ideal way of representing the diesel engine, or the gasoline engine, right? It's described by a 5-step process, and one is isentropic compression, and then of course there's some terminology, bottom dead center to top dead center. Okay, but it's compression, so you go from a higher volume, you compress the gas, okay? And then you have constant volume heat addition, right, to a new specific volume. But it's not new because it's constant volume. You just add heat at V2 or specific volume V2. Constant pressure heat addition. So now you expand it, constant pressure heat addition. You get an expansion. And then isentropic expansion from your volume 4 to volume 5, and then constant volume heat rejection back to its initial state. Sketch the corresponding PV and TS diagrams. So let's do that. P, V, and T, S. And again, when you do this, if you don't know where to start for state 1, of course you can just start right in the middle if you want, and then draw a picture. But the reality is, after you start going through all the step processes, the middle might not be the best place to start, and you would find there's more of an ideal place to go. So it turns out that when you do this one, the best thing to do is, I could start in the middle, and I know I'm doing compression, so I'm going this way. So let's start here, and then I don't have to draw 2 diagrams. Okay. So I'll say this is state 1, so I have a corresponding V1, and then I have isentropic compression. Now again, we can go to the PV diagram with the isotherms, right, and then the isentropic connection between the two. So we could have some isotherms that look like this with a isentropic, but if we do that, we're going to get something that looks like this. So what we're going to do is kind of a scaled, skewed one to show the isentropic, which is not quite as steep, and we'll have something that does this. Okay, so again, this is isentropic compression, and you went from V1 to V2, it's compression. Okay, it's isentropic, so their delta Q equals 0, delta S equals 0. And that's state 2. P1, P2. Then it's constant volume heat addition. Well, we can always write the ideal gas law, PV equals M R gas T. We have an ideal system. There's no mass in or mass out in the ideal case. So mass is constant. We have an ideal system, so we can use the ideal gas constant, right? And then constant volume, heat addition. Well, we just did the boundary problem with the ceramic cup. Heat things up, heat in, right? So heat in, heat addition, T goes up, T goes up. So we have some constant volume heat addition. So there's some Q in here. And I'm going to put it Q in, and then I'm going to put the 2-3 because there's heat in from going from state 1 to state 2. Then the next process is constant pressure heat addition. So then I have a P4, and I have constant pressure heat addition to volume floor. Well, this is also V3, and I can put a V4. So I have constant pressure heat addition, and let's put on here, again, there's some Q in, but let's put Q in 3-4. And then I have isentropic expansion. I've already drawn the curvature for this, so I should follow the same curvature for the expansion isentropic process. And I know I have to end back here, so let's just draw a dashed line with the same curvature, okay? And I know I have to end the constant volume heat rejection, so I have to have something like this. So now I have isentropic expansion, and then 5 to 1, I got some Q out, 5 to 1. And if I were to go back to some auto cycle pictures that we covered in not only earlier, but also in chapter 5, and the auto cycle again was for the spark ignition engine. You see how this looks? It kind of mimics what would actually be measured. Now the auto looked a little bit different, looked like this. And so we have adjusted it to have a constant pressure part and then deck that on to better mimic this. Of course, this is of the 4-stroke. Really, we have an exhaust and intake stroke. So network out, network in. Took work to exchange the fuel and get rid of the exhaust and put in a new fuel mixture. Okay. So now the TS diagram, again, if you don't know where to start, you can always put a point right in the middle and draw it. Right? So if you wanted to do that, you could start there, but what I'm going to do is isentropic compression. Well, we know that isentropic are straight up and down lines, right? So for the time being, let's just draw some straight up and down lines. And then we know that this is a large volume, okay, and low pressure. So if I put P1, V1, T1, then the question is where is T1 on here? Is it up here? Is it down low? But the reality is pressure always went up. So let's just put some T1 down here. And then we can also look at it from the context of a TDS relationship, right? So let's write an equation for a TDS relationship. So I have delta S equals mass CV, this is a big S, natural log T2 over T1, and then plus M R gas natural log V2 over V1. Well, V2 is less than V1. This is a negative number, right? Smaller number, less than 1. Natural log of something less than 1 is a negative number. Well, we know from 1 to 2, it's isentropic, so this is equal to 0. So I can bring this over here, right? Or let's just keep it there. A negative number, this needs to be a positive number for this to be 0. So T2 has to be greater than T1. So I just say here, and then I have a corresponding T2. I have something like this. And then I have S1 equals S2 isentropic. So isentropic. Compression, then the question is 2 to 3, constant volume, heat addition. It's constant volume, looking back up to here. Constant volume, V3, is the same as V2. Natural log of 1 is 0. T2, constant volume heat addition. I added heat, what should happen to the temperature? Again, we just did this. Constant volume heat addition, temperature went up, pressure goes, right? Pressure went up. So I should have some increase in pressure, and T3 is greater than T2, and delta S is a positive number. So I end up going in this direction. And I'm going to draw it like such. And put in my arrow of Q in 2 to 3. And then I have another constant pressure heat addition. Well, in this case, V went up at constant pressure, V went up at constant pressure, V went up at constant pressure, T went up. So again, I have an increase in T, but the slope will look a little bit different. Of course, I could always write this was for the constant volume. I could also have the constant pressure. So just as delta S equals M CP natural log, and then I'll do it for 3 to 4. So T4 over T3. And then with the second TDS relation with CP, it's a minus sign. M R gas natural log of P4 over P3. Well, it was constant pressure heat addition, so this is 0, and T4 is greater than T3. CP is different than CV, so you get a different magnitude of your deltas and S's, and the slope is a little bit different. How could you find, of course you could take derivatives of these things, right? So you get something that does that. Put in Q in 3 to 4, and then I drew this line over here. Maybe I should have drawn it up. Well, it's just, the fact is I have another isentropic expansion from isentropic expansion from V4 to V5. Well, isentropic S4 equals S5. And then I have back to my initial state. And draw my blue again. Q out. And I can write here isentropic. So there's my corresponding sketch of the PV and TS diagrams. Yes?
In the textbook, for the Q in and Q out, it's lowercase, and it's kind of inconsistent even in the textbook. It doesn't matter. Like, what's the difference between it being capital or lowercase?
Okay, if I use a big Q, just like in the energy balance, it's a good question. I'm really glad you asked this question. It's a really good question. Okay? It matters. What is the units of QI?
Kilojoules?
Joules, kilojoules, megajoules, picojoules. Joules, right? If I divide by mass, this whole thing, this whole equation, divide by mass, what is, I can rewrite this as a small q, joules per kilogram, in terms of heat. And so the textbook, because it's ideal, they forget about the mass, and they put everything in per unit mass form, and they use a small q. And the small q, in this case, QI equals QI over M. And it has units of joules per kilogram. And the textbook, on a lot of problems, example problems and whatnot, when it's ideal cycles, they put it in small w's, small q's. Likewise, what is the units of H? Kilojoules per kilogram. Specific, so in some ways they're giving like a pseudo-specific heat by using small q. But they use small w's, work per unit mass. They use small s's, small h's, small u's, of course, right? But they will use a small w and a small q.
And then small q also means like specific heat or...
Yeah, that's why I don't want to say specific, because usually it's written like that, and that's why I don't use the small q in any of my lectures, even though the book does it, because then I would be saying it's kind of a specific heat, which it isn't a specific heat, because its specific heat has to do with the change in temperature, and this q can be, in this case, what was that q related to? Phase change and sensible. Whereas CP, right, the CP part is usually sensible. So I don't use a small q.
Yeah.
But I'm glad you asked the question. That's why. They get rid of mass in all the equations. Doesn't matter when you get the thermal efficiency for the next part C?
I mean, yes, but
No, it doesn't, because you're going to get an equation with mass times a bunch of stuff, divide 1 minus mass times a bunch of stuff, divided by mass times a bunch of stuff. You take the mass out of the top and bottom,
yeah, it would just be how you said it.
and it will just cancel out. Or if you did it in small q form, you wouldn't have to do that algebra, because it would already be taken care of previously in the problem. Now, in a real process, there's some mass leak and things like that, so it won't quite work so well. It would not be ideal, so you would not want to do that small q. Okay, so let's go to part C. And it says derive the thermal efficiency, so eta thermal. Well, I can do this in many ways, right? I can do work out, right? Net over QH. Or I can say 1 minus QL over QH, while QH represents the heat from the high temperature source. So in this case, what is QH? It's QN 2 to 3 and QN 3 to 4. What is work out net? Well, that's the whole area in this curve, right? So I can get this, calculate this QN, and then add it to this QN, and then get the area under this curve and plug it into here, and I can do it like that, right? Well, to get the work out net, I need to get this integral. This one's easy because it's no change in volume. This one's easier because it's constant pressure. This one, again, is not that straightforward, right? Because I have to use my K's, and then it's a little bit more complicated. But anyways, I got this, minus this, plus this, gives me my workout net. So you can do it many ways, but why even do that? Because I can just use 1 minus QL over QH, so let's do that one. Thermal efficiency is equal to 1 minus QL, where QL is just Q out 5 to 1, and then I got QN 2 to 3 plus QN 3 to 4. Now the problem is, how do I you're gonna be asked a question, well, what does it look like in terms of temperature? So you're gonna need to do either an entropy balance or energy balance to get these as functions. Or you can just be clever, QL, constant volume process.
Without doing like the whole entropy balance.
CV,
a while.
delta T,
Okay.
QN, constant volume process, CV, delta T, QN, 3,4, constant volume process, CP, constant pressure, delta T. Basically, you just go straight to the partial of U with respect to T at constant volume equals CV. So then, of course, you can get delta U equals M CV delta T. Likewise, you can get the partial of H with respect to T at constant pressure equals CP. So you can get delta H, thank you. You can get delta H equals MCP delta T. And then we have a process where, in these cases, delta H and delta Q are related to the heat, but I don't want to go right there where you make that. I want to do an energy balance so you can kind of see a better connection between these two. So let's do the first one, Q out, 5 to 1. Q out, 5 to 1. What do we want to do? 5 to 1 entropy balance or 5 to 1 energy balance? Which one looks simpler from just a diagram perspective? Energy looks simpler, straight up and down line, right? So most likely mathematics is simpler too. So let's do that. Q out 5 to 1 via energy balance. So we do that. Energy balance, we go from state 5 to state 1, all the forms of energy in, right? Energy in minus energy out equals the change in internal energy from going from state 5 to state 1. What form of energy do I have in? Is there mass in? No, it's ideal system, no mass transfer, right? Is there boundary work? No, because it was constant volume. Was there heat in? No, the problem specifically said there's heat out. So this is basically nothing. And then what are my forms of energy out? Is there work out? Well, no, the volume was constant. I could put in the integral of PDV, but there's no change in volume. There was no mass transfer. It's ideal. Dual cycle, and all I have, so I get Q out 5 to 1 equals, and then I have this, so I have mass CV T1 minus T5. See, that one is pretty. This just came straight from energy balance. So I wrote my energy balance simplified to this equals delta U 5 to 1. Then I use the relationship for the change in internal energies coupled to. Apply this to my delta U there from state 5 to state 1. Yes?
It's supposed to be negative.
Yes. Thank you. Yes. My energy balance, I need the minus sign here, right? It was already there. Yeah. So it would be minus QO equals delta U. So that stays there with the minus sign. Thank you. Okay. Well, 5 to 1 was relatively straightforward. So let's do the QN. Okay. Now, again, we could ask, do we want to get QN from an entropy balance or an energy balance? Well, we just saw how simple it was here, right, from an energy balance. So let's do energy balance from state 2 to state 3. So QN 2 to 3 via energy balance. Okay, so QN, of course, sums all, the heat's in. Well, basically I get QN 2 to 3, no mass in, no boundary work, minus no mass out, no boundary work, no heat out, minus 0, equals U3 minus U2. Of course, this is my delta U 2 to 3. And of course, applying this, what do I get? Qn 2 to 3 equals mCV, and then I have T3 minus T2. So I have this piece, and I have this piece, and all I need is this piece, and then some algebra. So how do I want to do this one? Qn. How do I get Qn? Do I want to do an entropy balance or an energy balance? Yes.
Algebraically for the Q out from 5 to 1, if it wasn't negative on the left side, it would be MCV T5 minus T1.
Yes. You could multiply my minus 1 throughout the whole thing, and you could say Q out equals T5 minus T1.
Okay.
It
They
would
were
just
a
be,
little bit different forms, so I was getting.
yeah. So I'm not going to do entry balance because it will be a lot more difficult, and I want to get across the point with the delta H and the boundary work. We could get a function as a function of t and CP's, and in fact, we could go right here and we could do that. Right, we have our delta S from 3 to 4. It's constant pressure, use this one. And then I get my delta S, mCV, natural log, and this stuff. But then in an entry balance, I'm dividing by temperature. It just gets a little bit more messy. So let's just do an energy balance. And again, what looks simpler graphically? The nice straight line. It wasn't vertical, but it was horizontal versus some curvature, right? So Qn 3 to 4 via energy balance. So doing that, 3 to 4, do I have heat in? Yes. Qn 3 to 4. Do I have mass in? No. Do I have work in? Well, this is the question. Do I have a change in volume? Yes. But is it work in? It expanded, the gas did work, not work on the gas, right? But if you don't know, you can just say Q net in. And then you don't do the other side, then you're going to get a sign error. But it's work out, so we'll just leave it at that. Minus, okay? So I got my Q in, and then do I have mass out? No. Do I have work out? Yes, I expanded the gas. There was some work out by the gas. It expanded, right? There's work by the gas on the surroundings. Here's the power stroke. So I get some work out. And then do I get Q out? No, we already said it was Q in. And then that has to equal delta U 3 to 4. Now what is work out? Work out equals the integral of P dV. Well, pressure was constant, which equals P3, and then I got a V4 minus V3. So rewriting this, Qn 3 to 4 equals delta U 3 to 4, and then I have a plus P3 V4 minus V3. Well, the interesting thing is delta H equals delta U plus delta P V, which equals delta U plus P delta V plus V delta P. Constant pressure process, 0. P3 equals P4. So my delta H 3 to 4 equals that, which is this. So I have a delta H 3 to 4, which equals mCp T4 minus T3. So all said and done, Man, that clock being off is really goofing me up. Okay, so all said and done, what do we have? Thermal efficiency equals 1 minus, okay? I got this part, but I'll put in the minus sign and bring it in. So I have M CV T5 minus T1. And then I got an M CV, this part, T3 minus T2. And then I got a M CP T4 T3. And I can do this, and then I know that K equals CP over CV, and then I can play around and do some algebra, divide by mass, my masses come out of this side, right? And then I can do a ratio, and I can put a K in there if I want it, and rewrite it using K instead of CPs and CVs, and that's typically what is done. But I'm not going to do that algebra, it's just the next step. So I'm trying to demonstrate, have a process, draw PV, TS diagrams, understand that areas under curves here matter. There's process steps, each one has corresponding, each process step goes from a state to a state. There's a corresponding energy and entropy balance. Turn out for the Carnot cycle that it was a nice box, so it was better to do the TS diagram and do an entropy balance. But for most of the other cycles, you're better off doing an energy balance. You could do energy balance for the Carnot too. Okay, so this pretty much sums up chapter 9. So the score is already, it already closed on me. I'll do my whole phone thing. I was going to show you the grade distribution for midterm 3. It's much better. I'll do that next lecture after we finish exam 3. Any questions on this?